Hello and welcome to this recorded e-learning on synthesis options. My name is Frank Nelson. I'll be your instructor for this module. This module introduces many of the synthesis options that are available in the latest FPGA synthesis tools, including Xilinx's own XST. This module introduces the primary synthesis options and the concepts behind their usage. These options can have significant impact on the quality of results a designer will get when synthesizing for an FPGA. These options will impact the speed of your design and help you manage your FPGA resources. If you are an experienced ASIC designer or new to FPGA design, this module will help you use your synthesis tool to full advantage. This module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you build an efficient design that will use minimal FPGA resources and get good performance. These practices are designed to promote fast and efficient FPGA designs. After completing this module, you'll be able to identify synthesis tool options that can be used to increase your design's performance and/or reduce your design size. You should also be able to describe an approach to using your synthesis tool to obtain higher performance. Finally, we just wanted to note that the guidelines in this module are not specific to any particular synthesis tool or Xilinx FPGA family. In fact, many times we'll refer to instructions that apply to various synthesis tools that are very commonly used in the FPGA industry. This flowchart is used extensively as part of our Designing for Performance course. And in that course, our primary objective is to show designers how to meet all of their timing needs. In this diagram, the first four steps in the upper left-hand corner describe the high-level procedures that all designers must follow early in the design process. These include making good pin assignments, understanding what a reasonable timing objective is, build their HDL code so they can get the optimum FPGA resources in their design, and making good timing constraints to be used during synthesis and implementation. Step 5 is to choose a synthesis strategy and goal. We will talk about what that means a little later, but for now you should understand that this choice will direct XST to synthesize your design in a pre-optimized fashion using recommended synthesis options. This makes it easy for a Xilinx designer to get their design synthesized easily. However, most experienced designers would rather go ahead and have the knowledge to customize the options as they choose. So we're about to go into that in this module. Now, step 6 is to synthesize the design. After synthesis, most designers are evaluating the HDL code associated with their timing critical paths. This is very smart. As you'll learn, your HDL coding style has perhaps the largest impact on the speed and the size of your design. So the smartest designers are busy isolating their timing critical paths, that is, those paths that fail to meet their timing constraints, with their schematic viewer and then verify that their HDL is optimal. Now this might require the designer to add a pipeline stage, recode some components, or instantiate an appropriate component that their synthesis tool is not inferring. All of these design changes can now be made before a single implementation, that is a place and route, has been completed, and that saves our customers a great deal of development time. After fixing the design, most customers should consider using their synthesis tool to full advantage, and that's what we're about to go into. And after resynthesizing with different options, perhaps even synthesizing multiple times with different settings, most designers then complete their first implementation. So keep in mind that using just a single set of synthesis options may not be sufficient. After reviewing this module, you should be able to anticipate which of the provided synthesis options might work best for your design. And of course, your results may vary because every design is different. But after synthesizing, optimizing your HDL, and instantiating the necessary resources, it is our intention that you should not have to go back to the design stage and resynthesize again. Many new customers are disappointed that they're going to have to instantiate some of the most popular FPGA resources into their design and that their synthesis tool won't infer everything they want. Well, this is now pretty much standard operating procedure in the FPGA industry, and what I mean by that is that most customers are prepared to create highly optimized cores with the Xilinx Core Generator or the Architecture Wizard utilities and then instantiate those components into their HDL. This flow allows users to work around the limitations all synthesis tools have with regards to automatically inferring the best FPGA resources. The bottom line is that all of the high-end synthesis tools available for the FPGA industry usually do not allow inference of all of the best FPGA resources. Usually the latest and greatest will allow some inference support of the DSP slice and block RAM. Now, synthesis tools may allow some inference of these resources. There are plenty of exceptions, however, but usually only primary applications are inferable. For example, the block RAM resources are inferable for memories that only use a single block RAM or are not initialized and don't use the output register. Simply put, it is too difficult for synthesis vendors to keep up with all the possible configurations of a single FPGA resource and build the ability for users to infer all possible functionality. To aid customers in building a desired component of complete functionality, Xilinx recommends that users build these components with the core generator architecture wizard. And when I mention high-end synthesis tools, I'm referring to the most popular synthesis tools available for the FPGA industry, specifically Simplify, as well as Xilinx's own XST. While this module is not about how to instantiate the best resources, it is an important skill to be able to do so. Xilinx provides some basic information about instantiation of these device resources in the Synthesis and Simulation Design Guide. This document can be found in the standard ISE software documentation or at support.xilinx.com. The next step is to achieve breakthrough performance is to write the best HDL code possible for your design. To help you write better code, we provide 2 basic HDL coding RELs and 2 Spartan 6 and Vertex 6 HDL coding techniques RELs. All are free and available at the same location you found this recorded e-learning. So if you've not seen them, check them out. The last step is to drive your synthesis tool and the implementation tools to the best of your ability. Well, we'll discuss the proper use of the implementation tools in the Essentials of FPGA Design course and the Designing for Performance courses as well. But this module is going to try and teach you how to use your synthesis tool to full advantage. To get optimum speed, device utilization, and minimal power consumption, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use those dedicated resources. For example, most customers would think to build a FIFO with a block RAM, but most would not consider building a finite state machine with a block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA. The reason these resources are so fast is because they have a fixed structure and are not built with LUTs and registers. They provide as much as 3 times the speed and use the dedicated hardware resources to full advantage, which will save you LUTs and registers for other functionality you can build into the FPGA. This slide is trying to highlight some of the benefits of using good HDL coding techniques. Not only do users have to be aware that not all FPGA resources are easily inferable and that they have to make sure they are getting the best resources, but designers have to be able to find their timing critical paths and then recode. This is usually done by designers adding timing constraints during synthesis and then finding those paths with their schematic viewer. Likewise, while building their design, most customers know that they should use synchronous sets and resets and how to add pipeline stages. But in general, users have to think about the number of levels of logic they infer and the negative impact those extra levels of logic can have on the speed of the design. To help with this, we want to encourage you to listen to those RELs I already mentioned about basic HDL coding. These are the primary synthesis options designers are using to improve their system speed. Now we're going to talk about each one of these features in detail. They include timing-driven synthesis, finite state machine extraction, retiming, register duplication, hierarchy management, resource sharing, as well as physical optimization. Now these options can greatly impact your design speed and device utilization. As I mentioned, they're commonly used in a number of different synthesis tools. Now note that these options are included with the 3 major tools our customers are using, that is Simplify, Precision, as well as our own XST synthesis tools. You'll note also that in the notes of each slide, where is applicable, there are specific instructions on how to access the functionality within each of these tools. Well, as I mentioned, the first thing you should do is add timing constraints with your synthesis tool. This will enable the synthesis tool to work on your most timing critical paths and use whatever optimization algorithms it has included with it to help you out. In XST, this is done by adding constraints into an XCF file. This will use our standard period, offset in, and offset out timing constraints. Now, if you're not familiar with these constraints, we encourage you to check out the Essentials of FPGA Design course. But if you aren't going to be able to attend, go check out the constraints guide and you can learn more about them. Other synthesis tools also support these same constraints, and their entry is usually done either with a GUI or in a text file, but you're going to have to check out that synthesis tool's documentation. Now, we recommend never over-constraining during synthesis. This means you should only add the constraints you need and that effectively communicate your timing objectives. Don't make them too tight and don't make them unrealistic. In the end, over-constraining during synthesis can prevent you from getting the best result. Each constraint is entered on a clock domain basis, and we recommend that if your design uses related clocks, then you also make those constraints related as well. This will help the synthesis tool optimize your design best. So timing constraints will drive your synthesis tool to work hard to meet your timing objectives. But these same constraints can be used to report your timing results. So we recommend that you verify the timing estimates provided by the synthesis tool's reporting mechanisms. This might be provided in a GUI or in a timing report. With XST, this is done in a text timing report. This timing information is only an estimate because the synthesis tools use loading models and do not have any actual routing information. However, their logic delays are accurate because these are, of course, fixed in the silicon, and Xilinx makes that timing information available to the synthesis vendors. You can make timing constraints with Simplify using their Scope GUI. This will store your timing constraints in an SDC file. You should note that with Simplify, your timing constraints will be passed to the implementation tools via an NCF file. This is not wrong, but if you over-constrain or also make timing constraints using a Xilinx UCF file, you may end up with conflicting timing constraints. So, generally, if you are going to be adding constraints or editing your constraint values, we recommend using constraints during synthesis, but prevent the synthesis tool from passing those constraints forward. That is, exporting those constraints. This can always be done in the synthesis tools. You just have to look through the documentation and find the button in the GUI. Now, XST requires designers to add an XCF file to make their synthesis timing constraints. After synthesis, these timing constraints are not automatically passed to the implementation tools. So XST users are encouraged to enter their constraints again using the Xilinx Constraints Editor. The challenge is that if you make your constraints with the synthesis tool and then pass them to the implementation tools, you will have to resynthesize each time you make further changes to your timing constraints. Otherwise, they won't be seen by the implementation tools. And simply put, customers hate this. By not passing constraints, you only have to make changes to the UCF after you've added your constraints to the UCF file before implementation, and then re-implement a second time. This assures that between iterations, your netlist has not changed, and that you never have to worry about having two constraints with different values. This also saves you from having two sets of constraints to manage, and you having to resolve which constraints got applied to your design during implementation. So keep it simple. One set of constraints for synthesis, and one set of constraints for implementation. Over-constraining your design during synthesis means specifying a constraint that is tighter than what your system needs. There has been an old myth that this does not hurt. Well, a number of years ago it did not, but in the last 10 years, synthesis vendors have built in such effective synthesis options that the tools don't waste their time on unrealistic objectives. So even though synthesis with unrealistic constraints is fast, it is actually not trying hard, because the tool sees the constraint as useless. Now, as shown on the graph on the right, the green line, which is your estimated performance, and the red line, which is your actual performance, are very close to each other. This is seldom what you get. The important thing is to note that the performance increases significantly when the right constraints are used, that is, constraints that are realistic and helpful. Keep in mind that these are only the synthesis constraints. There is no change in the code, but much like the place and route tools, when your constraint is met, the synthesis tools will stop optimizing to save you time. So as you can see from this chart, the best way to use this to advantage is to enter only the constraints you need, that is, what your actual timing objective is. Likewise, some synthesis tools support a global frequency field. This is not recommended since it lumps all the paths to one timing objective and is simply put too simple. For example, with a design that has two clocks, one a low frequency clock and the other a high frequency clock, the logic for each domain will be optimized to meet the constraint. For a low frequency clock, the logic can be optimized for area, thus saving resources, while the logic of the high frequency clock domain can increase the area to meet the constraint. It is very important that specific clock domain information is available to your synthesis tool. So try to make your constraints realistic and accurate and complete. This diagram is showing you an example where timing constraints were used and not used during synthesis so you can see their effect. The example on the left without constraints used fewer LUTs and had a worst-case timing path that was slower, while the same design on the right with constraints has better speed, but uses more LUTs. These results are typical, and it is important for you to use the appropriate constraints on each clock domain so your overall design is not too big or too slow, but just right. This allows you to get the most logic into your FPGA and the best speed out of the design. So after using constraints during synthesis and employing the synthesis options to your advantage, designers then use those same timing constraints to improve their place and route results. Likewise, they can then use various implementation options to improve their timing. Now, we're not going to have time to discuss the various implementation options, but we do provide detailed instruction in the Essentials of FPGA Design and the Designing for Performance courses on just that topic. After the implementation options, if a designer still needs further timing improvement, their performance can usually be improved further with the use of area constraints. Now, we discuss area constraints and the use of the Planethead software, and the Planethead software makes area constraints a lot easier and more efficient, which is why I mention it. We discuss both of those in the Advanced FPGA Design course, and really there we just give an introduction of Planethead. But if you really want to understand area constraints and the most effective use of Planethead of all its functionality, I strongly encourage you to check out the Planethead software course. After adding timing constraints for synthesis, you can see that this Reed-Solomon design improved its speed by approximately 40%. That's the two leftmost bars. Likewise, after using the same constraints during implementation, the performance improves some more. And finally, after using timing constraints, synthesis options, and some of the advanced implementation options, the design speed overall doubled. This shows you the impact of the proper use of synthesis and the implementation tools can have on the performance of your design. Generally, finite state machine extraction or optimization is a good thing. Most synthesis tools will use the number of states and the number of inputs to re-encode and optimize this component. However, as engineers, we all know that the best encoding also varies by the number of transitions as well. And this is the limit of this optimization. So if you have a real octopus of a finite state machine, and you can probably imagine what I mean by that, you might want to consider building your own custom encoding. Now, I generally recommend that designers take the time to evaluate their machine themselves by using an enumerated type and then manually synthesizing their finite state machine for binary, one-hot, and gray encoding. This allows you to weigh the differences of each result for device speed and device utilization and makes the final decision possible for you to be made rather than letting some tool do it. Now, if your machine is small and simple, then sure, go ahead, use the finite state machine extraction functionality, but don't fail to still be an engineer and try to at least evaluate the machine yourself. Also, you should note that by default, synthesis tools will remove all decoding for illegal states when the finite state machine extraction is used. Now, this can be dangerous depending on your experience coding a finite state machine and your application. In general, you should probably turn on the safe finite state machine construction. This will use more FPGA resources, but will help you deliver a reliable design. Retiming allows the implementation tools to move registers forward or backward along a data path to improve your system speed. In general, this will improve your speed, especially if you have tried to pipeline your application, but can sometimes still improve your speed even if you have not pipelined. The only caveat is that this can allow your synthesis tool to rename nodes along combinatorial paths that are now no longer the outputs of registers. Recall that synthesis tools do not change the name of register outputs and that these nodes are most frequently used for debugging and simulation. You might remember that ChipScope and the FPGA editor are used frequently by our customers to debug a design after it has been implemented. In fact, many customers would say that it is critical that you be able to debug and analyze your design with these tools. But if you allow the synthesis tool to change the node names, which often occurs when the node is not the output of a register, then the node you may want to debug may no longer exist. This also happens when designers allow optimization across a hierarchical boundary. So don't forget about this caveat. It's a real pain to learn about it later on. So how should you use this option? Well, I might recommend that you allow retiming after you have at least performed behavioral simulation. Or if you could somehow allow retiming on a component basis, that would be best. But unfortunately, I don't believe any synthesis tools will allow that. Another option that does exist is to use the keep attribute. This would force the synthesis tool to keep those nodes so labeled. The only challenge would be that you would have to code this attribute into your HDL, and that would be some extra work. So consider doing it, hopefully after simulation, but if you haven't completed simulation, you want to do it anyway, try to use the keep attribute on those nodes you plan on testing later on. Register duplication is also commonly done to reduce fan-out on registers. This, of course, will improve the routing delays and improve your timing, but keep in mind that Xilinx recommends manually duplicating logic or registers. This will give you the ability to control the size of your design. Also keep in mind that if your synthesis tool allows you to set a global max fan-out, that this can make your design exceedingly large and often duplicate nets that are not creating a timing problem. The key is to understand that not all high fan-out nets will give you a timing problem, only those that are part of a timing critical path. So what often happens is the designer does some timing analysis and finds out after synthesis or after implementation that a piece of logic needs to be duplicated a few times. Now, this is easiest to evaluate after completing an implementation and creating a timing report with the Xilinx Timing Analyzer. That's a utility that's a part of the implementation tools. From the Timing Analyzer, designers can find the fan-out of a net very easily. Now, we discussed the use of the Timing Analyzer in the Designing for Performance course as an FYI. So when you duplicate a component manually, we also recommend that you name the duplicate logic _A_B, not _1 or _2. This will allow the implementation tools to not see the duplicate logic as being related, and thus allow the tools to move the duplicate logic further away towards the destination logic. This will assure better timing. If you numbered the duplicate logic, the implementation tools would see it as related because the tools see numbered bits as part of, say, a bus. So, letter duplicate logic, don't number the duplicate logic. You should also use an appropriate synthesis option to prevent duplicate registers from being remerged by your synthesis tool. So, for example, the best thing to do would be to go ahead and duplicate the logic and then use the keep attribute so that prevents the synthesis tool from removing the duplicate logic. One of the oldest features that still exists in all synthesis tools is hierarchy management. This was originally designed to allow designers to optimize combinatorial paths across hierarchical boundaries. Well, a lot has changed since then. Now, most FPGA designers are pipelining their designs and spending a big chunk of time simulating and debugging their design earlier in the design flow. So hierarchy management is now more like hierarchy maintenance. This means don't use the ability of the tool to optimize across hierarchical boundaries unless you've found nothing else enables you to meet your timing constraints. Optimization across hierarchical boundaries is discouraged because it allows node names to change, and that is counterproductive to debugging and simulating. This caveat is the same as the caveat I discussed earlier with retiming. In fact, most often if a customer is using this, it is across only one boundary between two specific components and is only after he has tried all other synthesis options. So be careful if you try this. Preserving hierarchy is now the norm of most FPGA designers and is the default behavior of all major synthesis tools used in the FPGA design industry. It allows you to easily locate problems with all debugging tools, simulators, as well as the corresponding implementation tools, Timing Analyzer. Now, maintenance of a design hierarchy is also required if you're going to be floor planning or using an incremental design flow. So note that if you register your lower leaf level boundaries, there's generally no need to flatten your design across hierarchical boundaries, and in fact this is recommended. Registering your lower level leaf level boundaries is usually done by inferring an extra register at the output of each component. That way there is sufficient time for the signal to go between hierarchical blocks in the design. So in other words, if the blocks are placed far apart, a long routing delay can be tolerated. Now also note that if you are maintaining your design hierarchy, it can limit the improvement of the retiming and register duplication synthesis options. However, this is not always the case. Every design is different. I still recommend trying to use retiming and register duplication. Resource sharing is generally an option that can provide some help if you have a lot of arithmetic operations in your design, and that is why it is on by default within the ISE and the XST software. But note that if your design does have a lot of arithmetic functions, you may want to evaluate your net delays. You may end up with more nets than usual that have a high fan-out, and you may want to consider manually replicating the associated logic. But generally, resource sharing is a good thing and should be turned on. Well, schematic viewers are terrific. In the end, they make it easier to analyze your design and are effectively linked to your synthesis tool's timing report mechanism. This makes it easier to not only display paths effectively and understand the HDL associated with making your logic, but isolating failing timing paths. It is important that you take the time to analyze the number of LUTs in series you have for each failed timing path. This is what is called analyzing the number of logic levels. This makes it possible for you to evaluate the associated HDL code and determine if you need to add a pipeline stage to your design to increase your design's clock frequency. Since your synthesis tool will reference your netlist logic names in the schematic, it is helpful to maintain your hierarchical boundaries so you can view the most logic with your schematic viewer. Coupled with your schematic viewer, most synthesis tools include a cross-probing functionality that enables you to jump from the viewer to your source HDL that is inferring the extra logic levels. This just makes it very easy to understand the impact of your HDL coding style and guide you onto where to fix your code. We cannot emphasize enough how important it is that you understand the impact of your HDL coding techniques. In fact, the best FPGA designers are very likely the best HDL designers. Cross-probing can also be enabled between your synthesis tool and the Xilinx implementation tools, specifically the Timing Analyzer. This also applies in case you're using Simplify or Exemplar synthesis tools and would also like to support cross-probing to the Xilinx Timing Analyzer. Now, this will require you to set some environment variables to enable the feature. To set this up, we recommend you refer to Xilinx Application Note 406 or XApp 406. You can search for this on our website at support.xilinx.com. Finally, some FPGA designers are choosing to work with the available physical optimization tools that are now available. Specifically, these include Synopsys Simplify Premier and MetaGraphics Precision physical software. These are extra add-on tools that do have a significant cost associated with them. In general, they're designed to group logic so that it is easier to make area constraints on related logic. Now, this kind of functionality is already available with the plan-ahead software that's included with Xilinx's implementation tools. However, some customers have told me that they believe these tools are better equipped to synthesize related logic to get better results than they have ever gotten. Now, these tools also provide some significant critical path optimization that some customers appreciate. Unfortunately, I personally have never had a significant chance to work with these tools. I have had several customers give me very positive feedback and have yet to have a customer tell me that they were not worthwhile, probably because their employer paid for the tool. But in the end, it will probably depend on your budget. If you're working with a very large, high-performance design, I would not discourage you from trying the tools because I've had some customers tell me how much they like them. So give it a shot if you have them, and let me know what you think. Now let's wrap up this module with a summary. First of all, your HDL coding style will affect your synthesis results and your overall design speed. So your coding style is preeminent. So make sure you check out those RELs. Infer resources whenever possible, but be aware of your synthesis tool's limitations. The synthesis tool attribute and this particular coding style may be required to infer a specific resource. Now, most are inferable, but many resources are going to require you to instantiate those components, particularly with the core generator or the architecture wizard. And as you get to the newest and the latest, greatest resources, this becomes more likely the case that you'll have to instantiate. Take advantage of the synthesis options that are included with your tool, and be aware of the caveats associated with them. Use synchronous design techniques always to make sure your design runs reliably, but also use timing-driven synthesis to achieve higher performance. And that's probably the most powerful of the different synthesis options we've described. There are some very useful resources available to you on support.xilinx.com as well as within our documentation. The Synthesis and Simulation Design Guide discusses some of the same topics we've discussed here, so I encourage you to pore over it a little bit. The XST User Guide is very helpful for example inferences of architectural resources as well as example instantiations. This is often what is most helpful to customers, so I would strongly encourage you to check this document out. It also goes into more detail about all the synthesis options that we've discussed here with an XST. The Constraints Guide is very helpful as showing you how to enter synthesis timing constraints. As we mentioned, this is highly recommended if you want to synthesize your design for high speed. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx Education link you see here. Now, don't forget to check out the HDL coding style RELs we're showing here. This includes the basic HDL coding style techniques, part 1 and part 2, which is basic design guidelines, describes basic stuff, basic design habits that good customers have. Also, look at the Virtex 6 and Spartan 6 HDL coding techniques, part 1 and part 2. These are designed to really help you optimize your code for specific architectures so you get the most out of these device families. And likewise, if you're working with XST, check out the XST synthesis options to learn a bit more about where all these options and other options are stored within XST to help you gain timing closure. Now, but whatever you do, please take a second and let us know what you thought of this REL. Just click on the icon on the next page and tell us what you thought. Again, my name is Frank Nelson. You've been listening to the Synthesis Options Recorded Learning. Again, thanks for your attention, thanks for listening, and thanks for your business.